We'll be continuing our work with finding integrals. At the end of this lesson, you'll be able to use a U-substitution to evaluate an integral. Okay, you'll notice I've got this big wordy definition down here, and I'm just going to, if you'd like to refer to it, that's fine, but I'd like to just talk about it a little bit. When we're taking the integral of a function, if you'll remember, we don't have a product rule, we don't have a quotient rule, like what we do in when we're taking the derivative. And also, if we've got parentheses, it usually presents an issue, because if it's to a third power, then we're going to have to multiply it out 3 times in order to work it. So if the problem, I kind of use this rule, if the problem looks like one that I'd have to use the chain rule on to find the derivative, then it would be one that I would do the U-substitution on to find the integral. The process of us doing this is going to be very similar to the U-substitution that we use in taking the derivative. There'll just be a few more steps that we'll want to add. So I'm just going to go ahead and start my problem, some of the examples, and then we'll just kind of work through it and hopefully make it make sense for you. Right, if we're looking at this first problem, it asks us to find the integral 2x times x squared plus 1 to the 4th power. Now in this specific problem, in order to work it with the skills that we know right now, I would actually have to multiply this out, x squared plus 1 out 4 times, and then multiply the whole thing by 2x, and then I could take the integral of both parts. Well, that is just a big pain in the butt. So instead, we are going to do a U-substitution, but this time what we're going to do, when we do a U-substitution, I have to replace every single thing in this entire problem with something that has a U in it instead of something that has an X in it. So this is going to be just a teeny little bit more involved than a normal U-substitution. Okay, thinking back to derivatives, when we did a U-substitution, we generally let what was inside of our parentheses be the U, and that's exactly what we're going to do on this specific problem as well. So we are going to let U equal x squared plus 1, and we're actually going to write down more steps than we usually do when we take the derivative. The next thing that I need to do is take the derivative of this, and I'm actually going to call this du. The derivative of u would equal 2x, and then right next to it I'm going to put dx, because we're taking the derivative with respect to x. So far I've just set up my problem. Okay, now what my goal is to totally replace every single thing in this problem with, again, something that has a u or a du in it. So if you'll notice, we just took this x squared plus 1 and we called it u. Okay, now you'll notice that du is equal to 2x dx, and notice right here I have 2x dx, so I can take the 2x dx out of the problem and I can replace it with du. So now what I'm going to write is, what do I have if I did that? Okay, the first thing that I have a u in the problem, and then notice I have done nothing with this 4 right here, so that 4 is still there, so it's going to be u to the 4th, and then the 2x and the dx are going to be replaced by the du. Okay, so I'm just going to cross out, we called this u, we called the 2x and the dx x, and I did put it to the 4th power. So you'll notice I have nothing left in that problem, and I just like to do that as a double check to make sure I replaced everything. Okay, from here, this is just a straightforward integral problem like we're used to. Remember, the du really is only there to let us know that our variable is u. So if I take the integral of u to the 4th, I'm going to get 1/5 u to the 5th. And again, the du just drops out when we take the integral of a derivative, drops out. So I just have 1/5 u to the 5th. And then my final step is, just like we do with derivatives, is we are going to replace the u back in. So it's just going to be 1/5 x squared plus 1 to the 5th plus c. And that is my answer. Notice we didn't have to, when I was done, take the derivative because we already took the derivative up there. Okay, let's try another problem, see if that made any sense at all. Okay, again, we'd run into some major issues here. I can't even take something to the 1/2 power and then multiply it by 3x squared. So with the skills that we have now, we would not be able to do that. I do see parentheses, which leads me to a u-substitution. So I'm going to let u be what's inside of the parentheses. Okay, my next step is I'm going to actually take the derivative of this part. So the derivative of u would be the derivative of x cubed is 3x squared. The derivative of plus 1 is just 0, and then I'm going to put dx because I'm taking the derivative with respect to x. Okay, now is where I'm going to start plugging in what I know. Okay, the x cubed plus 1, I'm going to go ahead and put it integral. The x cubed plus 1 is going to get replaced by u, and then I notice 3x squared and dx can be put together to make du. Okay, so I'm just going to put what I have. I have u it's still to the 1/2 power. And then the 3x squared and the dx, we're going to place it together into du. And now I'm just going to make sure I crossed off on my parts. I used the 3x squared and the dx because it became du. I used the x cubed plus 1, it became u. And I did include the 1/2 in my problem. So all of my stuff is gone in my rewritten problem. Now from here, all I need to do is take the integral. I will increase my power by 1, so I'll get u to the 3/2, and then we do the reciprocal out front. And then from here, all I need to do is to replace my u. So I'll have 2/3 x cubed plus 1 to the 3/2 plus c. And we are done with that problem. Okay, let's try another one. Again, looks very similar to all the other ones that we've been doing. If you want to maybe try this one, pause on the video and see if you can do it, and then come back and see if you got it right. That would probably be an awesome idea, but I'll just go ahead and work through it. I see parentheses, so I'm going to let my u be x to the 4th plus 2. And then I know I have to take the derivative of this. The derivative of u, the derivative of x to the 4th is 4x cubed. The derivative of plus 2 is 0. And then dx, because I'm taking the derivative with respect to x. Now it's time to start replacing things. Okay, the x to the 4th plus 2, I can replace that with a u. This 3rd power I'm going to keep. And then the 4x cubed and the dx, notice that they are again the du. So I can cross those out and put du in their place. So now I've got everything crossed out. I've got a new problem. I'm ready to take the integral. The integral of u to the 3rd would be 1/3 u to the 4th, and then I'm just going to sub back in my u, so I'll get 1/3 x to the 4th plus 2 plus c, whoops, to the 4th power, and then we are done. Whoops, wait, this should be a 1/4. Sorry about that, guys. So 1/4 u to the 4th. All right, so that problem is now done. Okay, problem 4. You'll notice this one is a big old mess right now. Nothing I can do. I can't use a product rule. I can't separate it because there's no plus sign, so I'm pretty much stuck. On this one, I'm going to rely a little bit on my knowledge of derivatives. I know that the derivative of tangent is secant squared. Because of that, I am going to let this part of my problem in some sort become my u, but I'm going to rewrite this first, just like when we do derivatives. I'm going to rewrite this as tangent x to the 5th secant squared x dx. I'm not going to rewrite this part, and I'll show you why when I do my U-substitution. So now, just like when we did when we took derivatives, we let our u be what was inside of the parentheses. So I'm going to let u equal tangent x. Okay, and then my derivative, the derivative of u is du. The derivative of tangent x is secant squared x dx, because when I take the derivative with respect to x, we write dx. Okay, so now let's go ahead and see if we can start replacing things. Okay, I'm going to cross this out, and I'm going to call that u instead. It's raised to the 5th power. And then secant squared x dx, notice secant squared x dx is equal to du. So I can cross both of those out because they are the exact same thing as du. Now notice I've got everything in my problem crossed out, so I'm set to go. Now when I take the derivative, the integral of u to the 5th, I'll get 1/6 u to the 6th. And now just rewriting this, I'm going to have 1/6 tangent to the 6th x plus c. And please get into the habit of just writing that 6 in the middle, because we are putting the tangent to the 6th power, and that's how we write it. So that would be my integral on that problem. Okay, let's try one more here. Okay, on this one, if you were to type it in your calculator, remember that when you type it in, you'd have to put parentheses around the 5x, which again sets us up for a U-substitution. So we're going to let u equal 5x. Then when I take the derivative of u, the derivative of 5x is 5 dx. Okay, now let's see if we can start replacing things in my problem. Okay, let's see here. This cosine, there's nothing to replace it with, so I'm going to leave the word cosine. And then 5x I can replace with u. And then the 5 and the dx, notice 5 and the dx when I put them together equal du. So I can cross those out and replace them with du. Notice that every single thing in the problem has to be replaced by something. You can't just ignore it. Okay, now from here, we know that the integral of cosine is sine, so it will just be sine of u. And now my last step is to put my u back in. So sine of 5x plus c, and that will be my answer. So hopefully now you have somewhat of an idea of how to use a U-substitution to evaluate an integral.